This video is about summation notation. So you may have seen these capital sigmas floating around in mathematics and wondered what they mean. So that's what this video is going to be talking about. So you generally have a capital sigma. There is a letter equals a number on the bottom. That letter, in this case I, is called the index. This tells you where to start. This letter on the top of the sigma tells you where to end. And then this a sub I is going to be something that uses the letter here. Usually, not always, but it uses the letter here, and then that's called the general term inside. And the sort of unwritten rule for summation notation is that you only move in integer blocks. So specifically, I start by plugging in 1 for my index I. So I go up here and I get a sub 1, where I just replace I with 1. Then I've plugged this in everywhere. Summation, right, should make you think of sum, which should make you think addition, which is exactly what we are going to do here. So I'm going to add whatever the next term is. So I check and see. 1, was that the last one? No. So I'm going to add another one, and now I'm going to change my 1 to a 2. So now I plug in 2 and get a sub 2, and then I check. Is 2 the last one? No. Okay, so then I'm going to add the next one. So then I bump up to 3. Plug in 3. Is 3 the last one? No, 5 is supposed to be the last one, right? So I keep doing this. So I add, bump up from 3 to 4, get a 4. Is 4 the last one? No, so I bump up to 5, get a 5. Is 5 the last one? Yes. So this original notation is equal to a1 plus a2 plus a3 plus a4 plus a5. So what you've got on the inside is your general term. The bottom down here is the index, and those sort of give you rules for adding a bunch of terms together. So let's just do a couple where we can sort of see with just some plain numbers what's happening. So here my index is j. I, j, and k are all very common indices. So this says start at 3, end at 5. So it's worth noting here that whatever this number is always has to be less than or equal to this number, and you only ever have integers when you're doing summation notation, right? So you're only going from some integer to some higher integer. So in this case, right, I take 3 and plug it in for j, and I get 3 squared minus 1. Notice that the 1 doesn't have anything to do with j, but it is still part of the term, so I write it when I plug in. Then 3 is not the final one, right? So I'm going to take this and add, bump from 3 up to 4, 4 squared plus 1, or rather minus 1. And then 4 is not my last one either. 4 is not my last one either, so I bump up to 5. 5 squared minus 1. Oh, 5 is the last one, so I stopped. So then I just clean this up. So 9 minus 1, 16 minus 1, 25 minus 1, or 8 plus 15 plus 24, or what is this? 8 and 15 is 23, 23 and 24 is 47. Okay, so let's try one more. You may want to pause the video and do this one on your own and see if you can get it squared away. Alright, so again, you might want to pause and practice, but let's just go ahead. So we start at 1 this time. Our index is I. We start at 1, so we get 2 times 1 minus 3 squared. And then 2 times 2 minus 3 squared. 2 times 3 minus 3 squared, and 2 times 4 minus 3 squared. So let me move a little bit over here. So then this is negative 1 squared. This is positive 1 squared, right? This one is 2 squared. This one is 5 squared. Right, so 2 minus 3, that's negative 1. 2 times 2 is 4 minus 3, that's 1. 2 times 3 is 6 minus 3. Oh, this should be 3. Right, 2 times 4 is 8 minus 3, 5. So then this is 1, this is 1, this is 9, this is 25, for a grand total of 36. Okay, so this is the gist of how summation notation works, and because this channel is about calculus, we are talking about it in the context of approximating areas. So these are the formulas for right endpoint approximation, left endpoint approximation, and midpoint approximation. So you may remember these, and if not, you may want to go look them up if you're interested in it. But these are some sort of cumbersome looking formulas for approximating the area under a curve. And you'll notice that what we're doing here in these formulas is you've got f of a plus delta x, and then f of a plus 2 delta x, and f of a plus n delta x. So you're adding a bunch of terms, right? And you've got this sort of coefficient in front of delta x that's indexing by 1 every time, right? It's sort of bumping up, bumping up, bumping up. So this, it turns out, we'll be able to write in summation notation, which is a lot cleaner than the version that we've got written here, and similar for all of these formulas. So using summation, you can turn these, summation notation, you can turn these into, for example, r of n is start at 1, go to n, and then add up delta x times f of a plus I delta x, right? So if you go look, right, a plus 1 delta x, a plus 2 delta x, a plus n delta x at the end, and you add them all up, that's exactly what this is telling us to do, right? And similarly, the midpoint approximation requires fractions, but you know, this is basically what's happening. So you may want to pause the video and try to come up with what ln should be. So again, this is the formula for ln, and we want to write that using summation notation. So you may want to pause the video and try to do it. So ln, I've got my sigma, and I am going to choose to start my index at 0 and go to n minus 1 instead of starting at 1 and going to n, unlike the other two. And if I do that, then it looks exactly the same as this general term, right? So if I start at 0 and go to n minus 1 versus if I start at 1 and go to n, that's the difference between left endpoints and right endpoints, right? 1, 2, blah, 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 up to n versus no copies, 1 copy, 2 copies up to n minus 1. But also, these expressions are not unique. I could have started this at 1 and gone to n. And there's a way to do it like this as well. So again, you may want to pause the video and try and see if you can figure this out. It will be delta x times f of a plus something here. And if I'm supposed to start at 0 and my first value is 1, what I'm really going to do is I minus 1 here. Right? So here I haven't changed anything about these, right, except the way they look. This says start at 0 and go to n minus 1 and multiply by I. This says start at 1 and go to n, but then multiply by I minus 1. That's the same thing. Okay, so these are usually not unique in terms of how you start and end your index. You know, some of the ways of writing it are cleaner than others. Like I like this one because I think it looks nicer, but this is also exactly the same thing. So this is how you use these summation notation to write endpoint approximations. And I just want to wrap up with a theorem and then one example about summation notation, which is if you've got m and n as integers, so remember that where your index starts and where your index ends is supposed to be integers, and the one where it starts should be less than or equal to where it ends. Then basically sums are linear, right? This is linearity of summation. So if I'm adding two general terms together and I'm going from m to n, that's the same as if I just did each of those things individually and then added the net result together. So you can break these apart over sums. You can also break it apart over constant multiplication. So neither of these two are very hard to believe. We're not going to prove them, but if you're multiplying by a constant inside your sum, you can just factor it out, do the sum, and multiply at the end. And then the last one is, what happens if your index doesn't show up at all? So here I've got my index j, and then I've just got a letter k in here. And before we fill, so you may want to pause and ask yourself what this is. And so to sort of inform what we're doing, we're going to go ahead and work this example so we can see what this looks like. So here's one with hard numbers, right? I starts at 1 and goes to 4, and I've just got a 2 on the inside. Not a 2i, right? Not an I squared, just a 2 with no I anywhere. So what you do is, you start your index at 1, you go to plug in 1, oh, there's not a 1 anywhere. So you just write down the general term anyway, right? And then you say, was 1 the last one? No, so you bump up. So now I is 2, right? and I plug in my 2. Oh, there's nowhere to plug it in. So I just write down the general term, but 2 is not the last one, so I bump to 3. I plug in my 3, but there's nowhere to plug it in. Is 3 the last one? No, so I go to 4. I plug in my 4, but there's nowhere to plug it in, right? And then I stop. So in this case, 2 plus 2 plus 2 plus 2 is 8, right? And you may want to try and generalize that to up here. So again, if you want to, you can pause and put it in. But in general, the answer is if I start at 1 and go to n and I've got k of something, right, then really what I end up with is just n copies of k. Just like down here, I ended up with 4 copies of 2, right? I'm going to write 2. How many times am I going to write it down? Running from 1 to 4, I'm going to write it down 4 times, right? So note that this is only true if you start at 1, but there are versions you can alter it appropriately. You know, if you started at 2, it'd be n minus 1 times k, for example. Okay, so this is a brief introduction to summation notation and a quick tie back to calculus in terms of approximating area under the curve.